one example. So let's look at this product, manufacturing engineers. You can help me at some point. So these are pistons and they have some rings that go around it, right? And this ring is the product that I'm trying to improve its quality or monitor its quality, control its quality. So the CTQ is the ring diameter, right? Diameter of that ring. So right now, the process, the actual process, has a mean of 74 millimeters and a standard deviation of 0.9 millimeters. Not too small, but let's assume that's the actual value. So the diameter of these rings, like let's say thousands of them, millions of them, the process, we estimate that it has that mean 74 and standard deviation. So it's going to look like that. So mean plus minus 3 sigma. Mean plus minus 3 sigma is going to be 74 plus 3 times 0.9. So it can go as high as, let's say, 76.7. Mean plus 3 sigma. And then mean minus 3 sigma is going to go to 71, I think, 0.3, right? So that's the actual parts. So if I take a sample size of 9 and monitor it's the average of these samples, right? We learned from central limit theorem that's gonna have the same mean, but the standard deviation is gonna change. So it's gonna be centered around the same line. So this is the distribution of the averages. They're gonna have still a mean of 74, it's the same. But standard deviation, as we learned, is going to be the standard deviation of the population divided by square root of sample size. So square root of 9 is 3, and then the actual sigma is going to be 3. So 0.3. And we know that we established the control limits based on averages, not based on actual individuals, because there is no guarantee that the individuals are normally distributed. What if they are distributed like this? So we always work with averages, and that's the mean and standard deviation of our averages. And if I am making a control chart for X bar, which is this guy, we know that the control limits are going to be, the center line is going to be just the mean. So the center line is going to be 74. What is upper control limit? For X bar chart. This is an X bar chart. Average of X bar, which is X double bar, or mean of X bar, which is 74, plus 3, could be something else, but we commonly use 3, plus 3 times sigma of that characteristic, that statistic, which is X bar. Sigma of X bar, we just learned it's 0.3, so it's going to be 74.9, almost 75. And what is LSL? It's 73.1. Same logic, minus 3 sigma. Okay, so these are our control limits. So when I take samples are coming from which distribution? This. Samples are coming from this, but what I'm plotting here, because it's the mean of, it's the average of each sample, it's coming from this distribution as a smaller variation. So my points are going to fall here within the limits. So I'm going to expect to see something like 1 point here, 1 here. These are all random, right? And every now and then I may actually get a point that's here, which is very unlikely because this distribution can go further down, further off, but getting a point after 3 sigma is very unlikely. If that happens just randomly, we call that the false alarm. We know that already, but this is what's happening. But let's say at some point, for some reason, mean of the actual parts, their mean has shifted. has increased. How do you think it can happen? So now they are, for example, so mu has changed to mu1, mu naught has changed to mu1. Now it's 75.5. Same standard deviation, same distribution, the mean, so they are all a little bit larger, right? The diameter is larger for all of them. So there is an assignable cause behind it, something has caused it, but we don't care about that right now. Let's say they're using the operator has started using a different mode, right? Mistaken. So when that happens, distribution of the actual part has changed. So this distribution that I had here is now here. But I don't know that change has happened. I'm still taking samples, plotting them on the same limits, right? I don't know that change has happened. Hopefully this control chart will show me that it has happened. But again, I take samples and the averages are distributed like that. So the points the points from this distribution will appear here in this area, right? Plus minus 3 sigma. So the new points are going to appear here, right? This area. So there is still a chance that when I take a sample, it falls here. So what's happening now? The process is out of control, but I think it's in control, right? So we call that a type 2 error. And the probability of that is beta. So of course, at some point, because the points are coming from this distribution, they're going to be distributed like this. I'm going to see a bunch of points out of control limits, and I'll be able to detect it. I'll be able to tell the process out of control, but it's going to take some time. There is a chance that I still see some points here and think that the process is in control. Okay. So beta is the probability that although the process mean has shifted, the point falls within limits. Beta is that probability. Okay, type 2 error. Probability of type 2 error is beta, which is probability that the point drops within limits, although mean has changed. Which mean has changed? Mean of the actual process. Okay, so today we're going to calculate that beta, and we're going to see how much that beta would be for different values of sample size. We want to see how beta changes when sample size changes. And what helps us do that is called an OC curve. OC curves help us see what's beta with respect to different values of n. But we also need to do something else. We need another parameter to be able to do that, and that's explaining this shift. So how much shift do we have here for the mean? 1.5, right? It was 74 before, now it's 75.5. So basically, mu1 is mu naught plus 1.5. I want to rewrite that 1.5, which is the amount of shift, as a function of sigma. Sigma hasn't changed. Sigma is just 0.9, right? What would be that? I'm going to say mu plus k sigma, right? What do you think k would be? So it's basically 1.5 divided by 0.9, right? 15 divided by 9, which is 5/3 which is 1.67. So it's mu naught plus 1.67 sigma. So that we call it K. So this is what's actually happening, and I'm trying to find the parameter K, which will help me in the next slide, calculating beta as a function of K, amount of shift. Because if instead of 75.5, the amount of shift was much less, for example, from 74, you would go up to 74.5, right? So the new line would be here. And the distribution of the averages would be further down. And it would be more likely that these points fall here, right? Or if the amount of shift was larger, for example, if it was 80 instead of 74, it would change to 80, the mean of the width of the origin. Then it would go all the way here. There would be no way that the point falls within limits. It would be impossible. And we would catch it first time. So beta would be basically very close to 0. So beta is a function of how much shift we have. And here we just try to express that shift as a function of sigma. The sigma was 0.9. So I did this to, my shift was 1.5. I expressed it as a multiple of sigma, K, which is 1.67. Any questions so far? All good? Nice costumes. All right. So here it's just that sigma is going to be still 0.3. All right. So the actual distribution has shifted from mu naught to mu naught plus K sigma. That's what has happened. So X bar's distribution originally, it was mu and sigma over square root of n. That's the value. So standard deviation is sigma over square root of n. We know from what we've learned before that UCL, upper control limit, we just calculated that. It's mu naught plus L, which was 3 in our example in the previous slide, and sigma of the averages, which is sigma over square root of n. And LCL is just that minus L, sigma over X bar. So beta is the probability that the average falls within these limits. I saw that in the previous slide. Given that mu has actually changed to some mu1, which is the previous mu plus some changes, some increase or decrease. So that's beta. What is that? It means beta is the probability that the point, the average that you took from the sample falls within limits if your mean has actually changed or shifted to a higher value. So if I want to calculate that, I use basic principles of normal distribution and standard normal. That part you need to worry about. If I simplify it, eventually beta becomes phi of L minus K times. So this is a formula you need to just learn and memorize or take notes. L minus K times the square root of n minus phi of minus L minus K square root of n. So in the example we just saw, L was 3, n was 9, right? And what was K? 1.67. So it would be basically phi of 3 minus 3 times that, whatever it becomes. So it's phi of something minus phi of something else. We read that from the table and we get a number. That number is basically beta. We'll see an example.
Why is L3 again? It's like 3 sigma? Or?
Remember when we were establishing control limits, we said control limit is mean plus a multiple of sigma or L, which is usually 3. So in the example we had here, UCL was mean plus 3 sigma of X bar. But we have already always used 3. Okay, so any questions now? Good. So again, beta risk. This is something we want to define now based on beta. Beta risk is the probability of not detecting this shift on the first subsequent sample. Beta was just the probability of 1 point falling within limits when the mean has changed. Beta risk is that, so the difference between beta and beta risk is this word, the first. So as soon as the shift happens, what's the probability that the first sample that I take after the mean has changed falls within limits? That's beta. And we just calculated that it's going to be that formula. So let's look at an example. Suppose that you're using an X bar chart with L equals 3 plus minus 3 sigma, the usual 3 sigma limits. The sample size is 5, and we wish to determine the probability of detecting a shift to mu equals mu naught plus 2 sigma. So in the example we had 74 plus, for example, 74 plus 2 times 0.9, which is 1.8. So your new mean has changed to 75.8. Basically. We wish to determine the probability of detecting a shift to that value on the first sample. So that's the beta risk. Basically that formula. Then, so L is 3, K is 2, N is 5. So we know that now. Beta is just using that formula we had of the L minus K square root of N. All right. And then it becomes P of minus 1.47 minus P of minus 7.37. What is this? What do you know from? By this, at this point, you should know what is this value. This is on a standard normal. Whenever I say phi, it means I'm looking at a standard normal that has a mean of 0, a standard deviation of 1. So 3 sigma is going to be 3 minus 3 sigma minus 3. And this is the probability of left-hand side of that point. So it's basically area under the curve for what point? Minus 7.37. This should be close to 0, right? So I expect that to be just 0. How about this one? Minus 1.47, somewhere here. That is probably some positive value. So 0.078. So there is a 7% chance that and the diameter of the O-ring increases from 74 to 75.8 in this example. There is a 7% chance that the first sample that you take, you will not be able to notice. Okay, so let's say you take samples every day. Okay, it happened. You took a sample, it fell within limits, you thought everything's okay, right? So what happened on that day? You didn't do anything, right? Because the point was within limits. But the actual rings were larger. So you produce a lot of, let's say your production rate is 1,000, for example. So all that 1,000 is probably too large. It's all waste, right? So there's a 7% chance that you will produce the 1,000 faulty or waste parts. Sometimes, so whether this to interpret this value, you need to look at two things. how often I take samples. In my case, it was every day. What's my production rate? And also, how expensive are my parts, or what's the cost of producing waste? Sometimes you're using raw material that is very expensive, right? So to produce waste with raw material that's very expensive, it's not a good thing. All right, but the probability also is not that bad. It's just 7%. It's only 7% chance. So when you want to see what beta is good, you should think about this. What's my production rate? How expensive are my parts? And how often I take samples? Okay. That tells you what's the actual risk, beta risk. Now let's look at this. This is basically the main thing we wanted to look at. OC curves, operating characteristic curves. So it shows you on the x-axis K. What is K? How much the mean is going to shift. How much the diameter, how much larger the diameter of the rings are going to get. And the y-axis is beta. You know what beta is? Probability of not detecting, or probability that the sample detect, the average falls within limits. And then you see the curve for different values of n, different values of sample size. Why? Because look at beta. Beta is a function of n. So you change n, beta changes. You change k, beta changes. So if I ask you, what's the probability of, or what's the beta risk? What's the beta risk if mean 74 increases to U1 equals 76.7. And sample size is 4. What is beta? What's the probability that the point falls within limits when the mean has shifted up from 74 to 76.7, and n is 4. And sigma is also, I'm going to give you that 0.9. The same example we had in the first slide. So what would you say? Use that graph. So you want to read this, but to do that, you need to know what's k, and n is also given. Let's see. Like that. So what do you do to answer this question? I need to find beta. Which one of these values? What do I need? I need to know which one of these lines I need to look at. It says n4, so just this line. Forget about the rest. Right? N is 4. So, and then you also need k. What was k? Amount of shift, which is 3 great. What is 3? Because 74 minus 76.7 minus 74 is 2.7, sigma is 0.9, and k is a multiple of sigma. So k is 3. 3 times 0.9 is that 2.7 amount. So k is 3, n is 4. What is beta? 0. Very unlikely, it's almost 0. So if I tell you I have decided to reduce because my beta is really small and our samples are really expensive and time consuming to do sampling and testing and all of that, I wanted to reduce the sample size to just 2. What is beta? So if someone in your company says, why don't you take a smaller sample? These are very expensive and time consuming. You say, wait a second. 3, n is 2. What is beta? Almost 15%. So k hasn't changed. K is 3. But beta increased to 15% now. When I changed n to 2. Because I shifted to the next line. I was here. That's the amount of shift in mean. I went from 4, which is here, to n equals 2, which is here. So now I go up. I see that corresponds to a beta of 1.5. Sorry, 15% chance of 5 to error. Beta risk is 15%. 15% chance that you take a sample, the first sample average falls within minutes. Okay, I think you got it. Any question? Confusion? So if you don't know what's going on, tell me what is the first thing that's confusing. That's a good way of asking questions. Anyone?
You found your k was 3 and our n was equal to 4. How you correspond those two together?
So I changed n to 2. This is for n equals 2. So first time n was 4, n was 3, so beta was 0. Then I changed, then I said, what if my n was 2? Then I shifted to this line, then it became 50%. So for n equals 2, this is 0%, this is 15%. I shouldn't show it the percentage, but it's more practical to explain, manage. Yes?
You decide which end to use.
That's the thing. Here I'm deciding which end to use. Depending on my process, how expensive the parts are. Yeah.
K.
So how do I find K? That's a good question. Here I just assume it's going to go from 74 to 76.7, right? But you should know the product, you should know the CTQ in practice to decide how much that K is likely to be. For example, let's say I have 2 molds, and there's a chance that the operators use the wrong mold, right? The first one produces diameter of 74, second one produces this. So it's for exam and for the questions like this, it's given, but in practice, you need to know what is a likely amount of change that can happen. So you should have all these tools in your toolbox, and when you go to practice, then you can determine K, you can determine all of this. Mu and sigma, you have already collected data, took large samples, you have determined process mean, process sigma. All right. But this is where you want to decide on the sample size. So if the shift is 1 sigma and n equals 5, now answer this one. If the shift is 1 sigma and n is 5, what is the probability that the shift will be detected on the first sample? N is 5. Let me erase these so you see better. N is 5. So you look at only the curve that corresponds to n equals 5. And shift is 1 sigma. What's the probability that, what's basically, is that beta? what is the probability that the shift will be detected on the first sample? Will be detected. What is beta? It will not be, it won't be detected. It will fall within limits. So this is the opposite of that. So this is 1 minus beta, right? So what is beta? By just looking at this, you should be able to, let me see, 1 and sample size was 5. Anyone? Anyone who can risk being wrong? So the amount of shift is 1 sigma, K is 1. So I look at here. N is 5, so I'm going to look at this here. This one. I see where this line crosses. I wish I had a ruler. Don't have it. Anyways, I'll do my best. So that corresponds to K equals 1. N is 5. So whenever these two lines meet, wherever, here, that corresponds to like 0.85. So beta is 85%. So with a sample size of 5, 1 sigma shift, which is very small amount of shift, small change, you're very likely that you will not be able to detect it. So beta is 85. Therefore, 1 minus beta is 15. There is only a 15% chance that you will take a sample, and as soon as this shift has happened, you will be able to see. So it's risky. How about this? The probability that the shift is detected on the second sample. What should happen for that? First one, you miss it. Second one, you get it. What's the probability of missing? Beta. What's the probability of detecting? 1 minus beta. First one, you lose it. So here I'm assuming that beta is 75. But let's say beta is 75. I think I didn't, if I do it like accurately, it's gonna hit it here. I don't know how. But let's assume beta is 75. Although it's 85. Yeah, first it's basically beta not detecting times 1 minus beta detecting. That's 19%. What's the probability that is detected on the third sample? First one, you miss it, beta. Second one, you miss it, beta. Third one, you catch it, 1 minus beta. Beta times beta. Rate to detect. First, second, third. Good. So now I'm interested in one value, which is, so here you see the probability of catching it on the third sample is 14%, second sample 19%, first sample 25%, right? But I'm interested to see for a given sample size, what's the average number of, what's the average place where I catch it? Like the first time, I take a sample, I get it, catch it on the first time. Next day, let's say I'm taking samples every day, and I'm talking about every month. The first month, first time you caught it. Second month, the third time, third sample you caught it. Next month, the fifth sample you caught it. But what's the average? The average, we call it ARL, and we learned ARL is 1 over probability of point falling out of limit, and here it's 1 over 1 minus beta. So for this example, it's going to be 1 over 1 minus 0.75, which is 4. On average, if you have 1 sigma shift in the mean and your sample size is 5, on average, you will detect it on the 4th sample that you take.